to introduce Masayasu Mayan to those who know Mimura. And he and I have never worked together, even though our research interests intersect a lot. But I do remember one thing from the first time he visited me when I was at Rutgers long ago. It was a few months before my son was going to be born. So we decided to call my son Epsilon. And for those of you who know him, as Philip does, he is now definitely 1 over Epsilon.
Yeah.
So Mayan's going to talk about colonial patterns formed by chemotactic bacteria in E. coli.
Thank you, Hans. It's really a great pleasure for me to be here, and also I'd like to thank the organizers to invite me such a wonderful workshop in INI. In the morning session of Monday this week, Philip Meiji gave a very interesting introductory talk before his main lecture. That is, what is modeling and what is a rule or role of models and so on. So I was so impressed by his talk, and also I'm very enjoyed. So today I would like to change a little bit the title, just modeling of colonial patterns. And of course, some of you knows me very well, Hans. I'm not a biological modeler, but I have been for a long time working in the analytical theory of reaction diffusion systems. But today, I would like to spend most of my time on the modeling of chemotactic E. coli from the viewpoint of the closed system versus open system. So today, this is my title. And let's first introduce the example of closed system and also open system arising in the chemical reaction. And this is one example of the catalytic isosomal reaction. So here is we have 2 chemical reaction processes, and V is a reactant and U is intermediate reactant, and finally P is a product. And we assume the situation in the isosomic reaction. That's why A and K reaction rate is a constant, very simple case. So this is a closed system. It means no supply from the V, from the outside. So this is a very simple reaction diffusion system. You say this is no surprise. And P is given here. So this is essentially this is a 2-component system. If you solve U and V, then putting here, then you can get P. So this is just a simple 2-component reaction diffusion equation. And if we consider the following initial boundary value problem in omega, boundary domain, and this is initial condition, and this is boundary condition. Here we assume the zero flux boundary condition. Then we already know the following result, and this is Hoshino in 1996. There is some constant V infinity such that U, this is the intermediate, reactant, tend to 0, and V tend to some constant. So this is without mathematics can be explained. But at first we said assumed behavior of solution is extremely simple from the pattern formation viewpoint. Furthermore, it is qualitatively similar to the one of the corresponding ODs. So this result is if we consider the OD, then this is easily obtained by using phase plane analysis, and for the reaction diffusion system we can get this one. Also, this result can be easily expected because the reactant V is initially supplied only. So you can see here is so V always decreasing, and this is U square. This is just linear. That's why if U and V is decreasing, so this is dominant compared to this one. That's why U tend to 0 exponentially. And then V is described by the heat equation asymptotically. That's why we tend to some constant. So this is easily expected without mathematics. Okay, so this kind of closed system is less interesting from pattern formation viewpoint. However, if you consider open system is supply of V from the outside, and in this case outside concentration is U star V star. Then the equation is given by the following, and F is the feeding rate. So if F equals 0, then the system reduces to the previous one. So this is a kind of supplying effect term. And then we consider the same initial condition and also same boundary conditions. When U star equals 0 and V star equals 1, for instance, then Pearson showed the following the paper: complex patterns in a simple system. What does it mean? This means the following: depending upon the values of F and K, you can see many different spatial temporal patterns. Okay, especially one of the typical interesting pattern is the following. So this is the occurrence of a self-replicating spot of U. Okay. So this is 1D from 2, 4, and this is 6, and I don't know if this is 8, something like that. And this is spot 1, 2, 4, like this, and this is 3D. Okay. So Pearson emphasized about the following: if we consider a closed system, it's very simple, nothing happens. But on the other hand, if you consider open system, so open system generates a very complex pattern. And then these results suggest that the closed system seems to be the less interesting from the pattern formation viewpoint. On the other hand, open system may generate unexpected, diverse, complex spatial temporal pattern. So many. And so the people who are interested in the reaction diffusion system, we are very excited to understand this kind of pattern. Okay. And then for this reason, many reaction diffusion people, including myself, had changed their research target to open reaction diffusion system. To tell the truth, I had abandoned such a closed system as a waste almost 20 years ago. I just forget it. Okay.
Could you? I actually never saw a system of equations that describes closed system. Could you show an example?
Closed system example is I told you this one.
This is closed.
This is closed. Closed means that it is no supply from the outside. Just we is supplied initially. That's all.
But in a sense, it's open, isn't it? Because you're degrading U into P.
Yeah.
It still consumes energy, isn't it?
Which one?
Well, like if you imagine molecular reactions behind
yeah.
the system, the reactions still consume energy.
What does it mean?
So in thermal equilibrium,
yeah.
The system will be very different, no? So your definition as open means like supply of material.
Yes, and also consuming.
Yeah, but both closed and open, and in your formulation, they still need energy.
Yeah. But in this definition is just thinking about the sort of the energy supplying from the outside to the system. That is an open system. But if the reactant is supplied only initially, that's all. Then and so it's decaying. Okay. So that is so closed system in my definition.
So essentially, the free energy is supplied with the reactants in the beginning, and then everything can just decay and that.
Yes.
Oh, no. If you don't supply energy, there's no pattern possible in the end. The steady state should be just homogeneous.
Yeah.
Yes.
Yeah, exactly.
Okay. So, oh yes. However, this is today's talk. I have found that several experiments, even if these are closed systems, could generate various complex patterns. And I would like to show one example today. That is this one. So this is a very beautiful flower-like pattern discovered of nature in 1995, observed by Badlin and Berg. And then, so this is a sort of the 1-point inoculation. So this is sort of petri dish, and here is agar, including nutrient. And when we put 1-point inoculation here, so this is bacteria. Take the nutrient, including agar. Then the growing, and then eventually bacteria make a colony. Okay. So this my definition. This is a closed system. Okay. That's my definition, because this is only the the nutrient, including this one. That is no supplying from the outside. Okay. Okay. Yes, it's a closed system in my definition. And looking at this one more carefully, so this is I heard this is artificially colorized, but original one is like this. And you can see that white spot, and the white spot is is called microcolony, roughly 50,000 cells. And so, for me, this is very beautiful pattern. Okay, and look at here. There are two different types of geometrical structure. One is this kind of one, very nice checkerboard. The other is so like this. Maybe you can see something like this. Okay. And then by using this kind of patterns, we say chevron pattern. So this is Japanese, very beautiful. Okay, so this is a so-called chevron pattern, and I'm surprising bacteria generate this kind of pattern. How can we understand? That is my, first motivation to be interested in this pattern. And this Badlin and Berg published only 2 papers. I don't know why, only 2 papers. One is 1991, just 1905, and the complex patterns formed by the motile cells of E. coli. The other is the dynamics of the formation of the symmetric patterns by chemotactic bacteria. And then in these papers, they say the following. Yes, this E. coli is a chemotactic strain. That's first thing. And then E. coli cells, aggregate in response to the gradient of attractant which they excrete themselves. Okay, this is a chemotaxis. Okay. And third one is such an attractant is a chemical sensed by the aspartate receptor. Okay. So this is the so-called chemotactic bacteria. And then they also said the excretion of the attractant can be triggered by oxidative stress, as oxygen is limited at high cell densities. Aggregation might serve as a mechanism for collective defense. That's why they begin to aggregate. And then they showed 3 different patterns depending on the concentration of succinate nutrient. This is 1 millimole, so it's a very nice 1 point inoculation, then very nice disc shape. This is we say trivial pattern. But if this is a double, 2 millimole, then you can, maybe it's very hard to see, but so like this, okay? And then this is a 3 millimole, almost similar, but the quasi sunflower pattern. Doesn't change. Thank you, Philip. Okay, so depending upon the concentration of succinate, they show the 3 different patterns. Okay, and more carefully, looking at the pattern. This is a 2 millimole. So look at here. So at first this is a spot, and the second, like this. So this almost synchronized, okay, like this, and expanding here. And also look at here. If the width between the 2 spots bigger, then new spot appears. Okay, so like this here. So this is a typical phenomena of this kind of pattern. So we call it rectangular lattice clusters. And I will show some dynamics or formation of this kind of pattern here. So this is a sort of cluster. And then some of the spot moving this periphery, and this stay there, and this is a new cluster. And then some of group stay there, and it's moving this way. Come on, and maybe here. So like this. Okay, so roughly speaking, we can say the following. This is, the red circle. This is a sort of the steady cluster, and this is moving here, and to form a new cluster, and then probably this becomes the steady cluster. Okay. So something like this, and steady, and so something like this. Yes?
Do you recall what the spatial scale is, the spacing between those?
Which this one?
For example, pick any 2 of those.
I don't know. Why you ask me?
Because I don't remember.
It's 3 millimeters.
It's microns, but I don't know exactly.
This is like a micron, okay? Or 0.1 millimeter. Okay. So how about this one? This is a 3 millimole, okay? As I said, this is a hexagonal lattice cluster, so like this. So essentially the same, but different is this alternative here. And it's very hard to see, but this in this situation also, if this wider is wider, then new, spot appear. So this is the first experiment done by Badley and Bag. And then roughly speaking, we have 3 levels. One is the microscopic level, so like this. And this is mesoscopic here. This is a sort of the point something millimeter. And this is a centimeter. We can see. this kind of pattern. And this naive question is how and also why chemotactic bacteria form such a very beautiful patterns. And then Biden and Berg conclude in the maybe second paper, at the end, they say the following: such patterns do not occur due to the genetic control. That is, a specialized morphogenetic program is not required. That is, when the following four elements, nutrient consumption and cell growth and excretion of attractant and the chemotactic mortality are combined in a certain way, then these patterns, these could generate complex spatial pattern in a self-organized way. That is their conclusion. So naive question for this gives us a following question: the system generates such a complex pattern even if it is a closed system. Okay. So in a previous chemical reaction, in a closed system, nothing happens. But here is the system generates a very beautiful pattern. Why? We can understand. Okay. So in response to Bodin and Berg's claim, many macroscopic PD models have been proposed in the world. Let me show some examples. So from 1992 to 2006, Israel group and also US group, Japanese group and also Russian group. They propose macroscopic PD models. And so they showed a very nice spot pattern. And then their models strongly suggest that the occurrence of spot pattern is due to the chemotactic effect, and it's so-called chemotaxis-induced instability. Okay, this is one of the instability to generate such a spot pattern. However, I have some question to their models. One is the following: formation of spot pattern seems to be qualitatively different from experimental one. So this is the model done by Japanese group. So here and this is becomes here, and this is becomes here, so, and so on. So they, their model does not show this kind of cooperative, work. Cooperative means there is some group, some class there. So some of them you stay there, and this is moving this way, and this is you stay there, something like this. Okay, this is very nice cooperation. But in this model also we cannot see such behavior. And second one is a transition of geometrically ordered patterns when the nutrient concentration increasing only. So this 1 millimole, 2 millimole, 3 millimole. Okay. And then the model did not explain such a transition. Mm-hmm. Okay. And also we are very much interested in the chevron-like pattern. Also, as far as I know, their model did not generate this kind of pattern. Okay, so at first I'm thinking about this problem. Then in this talk, I'd like to discuss about this kind of problem. The first one is the experiment is a closed system. Nevertheless, why does it generate so distinctive pattern? So I can explain later. And second one is the system generates geometrically different patterns when the initial concentration of nutrient is varied only. How can we understand it? I can explain. And finally, how is the mechanism behind the occurrence of chevron-like pattern? Okay, so this is very hard problem for me. Okay. And then this is very important thing for me. There made Badley and Bag's experiment on colony pattern. No, not by, okay. So perfect and beautiful. Extremely fun and fantastic, okay. However, the information from these patterns is insufficient to do modeling, at least for me. So too beautiful, okay. So no idea to make a model. Then I had a very nice, information. Experiments of this chemotactic coli have been carried out in Japan. And this is, Sakurai, Dr. Sakurai. He, received this kind of, E. coli from bug. Okay. And he showed the following. Unfortunately, his experiment is not so beautiful. Of course, at first he showed depending on the initial concentration. He also said at first circular waves like this, and this kind. So this is, I said, it is a pseudo, rectangular, and so this is the hexagonal one. And of course, this is already observed by Badley and Bag. But still, he increasing the concentration here. Then coming back to this one, and also nothing happened here. And please look at here. This is his experiment. It's very dirty, so like this. And this is very nice hexagonal, but this is very funny. But this is very important for me to do modeling. And also this is a 10 millimole, is just a very simple one. Okay. So roughly speaking, and when you including the concentration of nutrient here, so at first very simple one, and so the non-trivial one, and eventually coming back to the simple one. So that is his story. Okay.
Question?
Yes.
Was he able to measure by some means the cell density in those different patterns? I.e., what's the number of bacteria per unit area in the different patterns?
No, I don't know. Okay, so now let's me show the our model. So at first, okay, so this is 2010, okay, and this too is my former PhD student. Okay, so at first, very much important assumption is the following. Bacteria possess internal state of two phases. That is active and less active phases. So I said that this is sort of less active. So this is very much active. So mathematically, I separate two different bacteria from the internal state point of view. Of course, it's same one. And then active cell and less active cell convert each other depending on their environment. Okay, so roughly speaking, if nutrients is so high concentration, then you do not change to W. If the very worst environment, you change to W. Okay, understand? This is yes, please.
Coli, are those bacteria known to have those two states? And is the pattern formation process unique to E. coli?
Okay. I don't know, but in my model, we just, use only two phases. I don't know.
Wait, but you said high nutrient is is more active and low nutrient is less active.
Yeah, that is the data. So we assume.
That's opposite of Dicty.
No, for instance, if you have a lot of money, okay, very good environment, so you can walk around, okay.
But you also might expect that if you're in a good environment, you stay still to enjoy the environment.
No. For me, so I'm going out to have some pub or something like to drink. Okay.
Well, it's just dictyostelium, it goes the other way. That's
Yeah, yes, one possibility. Yes. Okay, so, and only active cells are moving, growing, and secrete chemical attractant. This is I define you behave like this. On the other hand, W less active cells do nothing at all. Just looks like a sleeping, okay, or stay there. So we introduce 4 unknown variables: U, active phase cell, and W is less active phase cells. N is a nutrient concentration, and C is attractant. So only 4, the unknown variables. And so I will not touch with the derivation of the model. Just I show the result. Okay, so U is the active phase cell, U here. So this is a random walk. This is growth term. And this is the chemotactic term. And this is conversion term. Okay. And you convert to W, but W is just this minus and this plus. And I told you, W do nothing at all. Just to convert, that's it, okay. So no this one, no this one, and no this one here.
Doesn't it come back as well?
Okay, so usually if you add, the nutrients, so come back. But in this experiment, just look, okay.
Okay.
For instance, this is maybe BN, so W, something like that, okay. So you can see this is a sort of no surprise. So in my definition, this is a closed system. Okay. Okay. And then we have to assume the function of G, chi, and N. At first, so this is growth rate. This is growth rate over here, and growth rate is has the following property. Growth rate is a non-negative bounded monotone increasing in U and N, with GU not equal naught. And for simplicity, we assume GUN equal G bracket U times N, and GU is like this, okay. But if U star is 0, so this is a constant. But in my model, so when U is small, so G is almost 0. So biological speaking, I just assume the oxidative stress occurs. Okay. But don't ask me how value of U star. I don't know. Okay, so this is this growth rate assumption. Now how about AN? This is conversion rate. So here, so I maybe this is my assumption. AN is monotone decreasing is like this. So if N is in a very high concentration, N is almost 0. So you doesn't convert W, okay. But if N goes small, so very low density, low concentration, then this is convert to W. And this is monotone decreasing. In my model, in my model, okay? So it is very similar to my behavior. Okay. So important thing here, this is chemotactic sensitivity function. This is very important, the function here. So there are some possibilities for the sensitive function. One is the chi c is a chi naught times c, so the chi prime c is just constant. And the second is chi prime c is monotone decreasing. And here is the chi c is given by this one, depending upon the value of m. And if m equal 1, and m if to compare the following, if m equal 1, then chi prime is a monotone decreasing. This is well used in modeling for the other people. And here is so m equal 2. At that time is this is at there's some peak here that is monotone increasing and decreasing. So for large C, same behavior, but when C is small, different. Okay. So this is so-called cooperating binding. Okay. So now we consider. So I told you I was my background is mathematics. That's why at first we are consider about the initial boundary problem here. And then, so this is initial conditions, and this is boundary condition. And if we can solve this equation, then putting u and n is here, and w, and initially less active. Less active cell is not no there. That was just 0. So you can get w integration from 0 to t. That's why you can get W. So this is essentially 3-component system for U, N, and C. Okay. So the first question was, the experiment generates spatial pattern. Although it is a closed system, how can we understand it? So this is a theorem done by this is a Polish group, and this is France. And if the solution is uniformly bounded in time, there is some constant n infinity such that u tend to 0, n tend to some constant, c tend to 0 exponentially in L infinity norm. So this is very delicate, expression, because depending on the spatial dimension, if you choose a very funny initial condition, we can have a sort of blow up in a finite time. So this is just mathematics. But if the solution is uniformly bound in time, so we can get this one. So this is nothing happen. Every solution tends to the constant. Okay. So yes, our model is a closed system. So it means no surprising. The asymptotic behavior of a solution is quite simple, in the sense that no pattern formation occurs. Particularly, U active cell tend to 0. Okay. So can you imagine? So usually active cell is the nutrient is become lower and lower. So active cell convert to W. So in this system, no active cell. Yes, please.
Related to this, I have a
question, maybe
Yes.
a bit technical about. So in your videos, initially we saw the omega was growing. Omega, like your domain was growing.
Domain grow, no, domain fixed.
The domain was fixed in the experiments.
Yes.
Petri dish.
It's the wave that's going out.
Okay, it's just
Petri dish.
okay.
Yeah,
It's just a
like
way
a Petri dish
okay.
is like this.
Okay, all right, okay.
Okay, so however, the total density U plus W, this is very important because this is the total density of cell. Okay, that's why how is the behavior of its spatial profile of U and W. And then this is the second theorem. There are some n infinity and W infinity such that UNC tend to this one and W tend to this one. And and W is given by solving this equation here. And I told you so U exponentially tend to 0. That's why so we can get something integral. And it's very funny because for if you submit this result to the mathematical journal, probably this result will be accepted. However, if you submit this, the result to the biological, journal, probably reject. Why? Because the important thing is W infinity. What kind of spatial profile of W? Mathematically, we could say W tend to this one. That is no information. So this is a total difference between the mathematical journal and also biological journal. So we have to know what kind of this one, maybe chevron pattern or other something like that. That is important. Mathematics says, okay, there exists. That's it. Okay, so the important thing is here, okay? What is the final pattern of the colony? That is given by this one. Okay? So, the important thing is to know the spatial profile of W infinity, this one. And then we move to the second question. Does our model generate geometrically different patterns observed in experiments when the initial concentration of neutron is varied only? So in the experiment 1 millimole, 2 millimole, 3 millimole, that is. And unfortunately, no mathematics, I'm sorry, it's very hard problem in a rigorous way. So we have to rely on the reliable numerical simulation, unfortunately. And thanks to 3 guys, so it means that so this Japanese, he is expert in the finite difference method. And second one is the finite elements method. And third one is this is Martin is a finite volume method. And I asked for them to solve the same problem. Okay, and if there is some difference, so we discuss. Okay, so this is in this case it's reliable numerical simulation. Okay, so now move to the numerical simulation here, and we use this one. And at this moment, don't ask me why I use this one. But I used this one, okay? Not monotone decreasing. And then, so this is some parameter or functional here. But if you are interested, I can explain later. But the important thing is N naught. N naught is the initial concentration of nutrient is a free parameter. We, okay, actually this is a bifurcation parameter, okay? So we just change N naught.
Good question.
Yes, please.
I won't ask about the chemotactic sensitivity, but your G of U says that they're growing only if there are enough of them around.
Mm-hmm.
Right?
Mm-hmm.
You have a monotone increasing function.
Yes.
That means that per capita growth is actually increasing with density. How does one understand that?
Wait a couple of minutes, okay? I can answer. Okay, so at first, what I want to check is the following. Experiment suggests that when n naught is small, quite small or large, then the resulting colonies exhibit quite simple pattern of ring or disc shape. So like this and like this, okay? At first, I want to check how about our model, okay? And then so chi naught is this chi naught is 0.22, and n naught is small. This is 0.6. And then if you numerically solve the equation, you can get u is like this, and w is like this, okay? And mathematically speaking, when t go to infinity, not large time t, this is disappear. So only you can see this one, okay? And also this is 1D case. 1D case is this is w here, and this is u. This is active cell, and this is a nutrient, and this is a concentration of attractant here, and this is moving this way. And if you think about, I mean, the rectangular domain here, so this is also planar wave. So it's moving this way, it is moving this way. This corresponds to this one. Okay. So this is the numerics. So numerics says is for small n naught is nothing happen. Very simple pattern. Okay. And when n naught is small, then the chemotactic effect seems to be rather weak. Okay, and then in order to check this one, I consider the system when chi not equals 0. So this is 0. This is 0. So just we consider very simple two component system u and n. Okay. Then same I mean concentration of nutrient here. So w is here and u equals here, and this is n. But this forget this one, n here. And then planar wave also appeared, and also like this. What does it mean? This means is that for small n naught, chemotactic effect does not influence on the system. Okay? So the disk pattern is basically formed without chemotactic effect. Okay. On the other hand, when n equal n naught is large, the situation is similar. So at that time is, of course, n naught is very large, so u is increasing, and u secret c, so c is a very big one. So but the chemotactic effect becomes smaller. Okay. So like this. Okay. Okay. So for these limiting cases, the resulting pattern are discussed by a simpler system in the absence of chemotactic like this. Okay. And this is so I already discussed about this kind of one, 2000, 2003. This is my name. And the very important thing is following. Okay. In the absence of chemotaxis, we have the instability. Okay, we have the instability due to this term and this term. So, for instance, if n naught is 0.6, so yes, this one, so that like this one. But if n naught is 0.8, a little bit big, larger, then this is a sort of planar instability occur, and this is a kind of fingering pattern. Okay.
I'm sorry.
Oh, sorry.
Explain what this is? what is driving this pattern formation? Is it just the oxidative stress, or what?
Okay. At first, this is just two-component system. Okay. So please forget that the original model, original behavior. But this is we just neglect the chemotactic part, only the U and N. That is okay. And then if N naught is small, 0.6, then we can have a very nice planarly stable the wave. And this is N naught a little bit bigger, then this becomes unstable. But don't forget, this is still in the absence of chemotaxis. Okay.
So this is basically directional solidification.
Yes, solidification. Yes, that's right. That's why so it is planar instability.
What if you put in a surface tension instead of chemotaxis? Wouldn't it do the same thing?
Chemotaxis is the next part. Okay.
But are you going to show surface tension?
No. That's so of course, if we're interested in surface tension, so we have to think about sort of interface problem. But now just we solve the numerical, solve the reaction diffusion equation.
Because it'll have a similar effect. Surface tension, basically, it's cell-cell adhesion.
Yes. That is sort of lateral inhibition instability. So I found this one from this one, then coming back to the original system with chemotaxis. Okay, then and not increasing. At first, this becomes unstable. This is a U, and this W is a sort of like a solidification, is like a fingering pattern. Okay, so this is sort of the bifurcation of the two-component system. Or roughly speaking, of course, this bifurcation does not depending on the chemotaxis effect, and not okay. And then, and not increasing. So this is a sort of the, moving here, but this is becomes unstable, like Hopf bifurcation. Okay, Hans is okay. This is Hopf bifurcation. So I thought this is just moving here. So this oscillation like this. So this is another.
But it's an oscillation in space.
No, oscillation is space, oscillation in time, okay? Space, okay, but time. So at first this is moving in this one, okay? And this direction, okay? And then this oscillation. So here. So there are two different types of instability occurs. One is this one is this is lateral inhibition. This is sort of chemotactics in this instability.
But you get the same thing with surface tension because it's a capillary instability.
Yes.
If you look at Beckhofer's thesis, he has this transition as a function of the surface tension.
But okay, but now we're interested in sort of this fingering patterns instability by using bifurcation theory.
I'm a little bit confused.
Yeah, please.
If you go back one slide before, just one more page, right? This model, compared to the very first model you showed in the first slide, this is a closed system, right? So if we take again GU to be, let's say, U, and AN to be constant,
yes.
this will be.
Sorry. Yes, yes. If this is moving, this direction,
Yeah.
and hit, they disappear. So U tend to 0.
Okay. And then, but in this case, AN is a decreasing function.
N is wait a second, decreasing function, yes.
So I would assume that it will go to 0 much more faster compared to the original, when I take an to be constant. So let me ask this way. So what do you think comparing those two model, if I take GU2 equals to U and an equals to constant, what is the difference between that model and this, this model will produce the pattern, but not the other one?
Probably, when A is constant, we have the same story.
Yes.
Important thing is G.
And GU is not U.
G is a sort of like this, okay?
Okay. It's like a...
Okay, yeah.
Comment? You didn't actually prove that in the first model, you just proved that asymptotically they went to those solutions, but you didn't say anything about the transient behavior.
Yeah.
So that may
It's a
account for the
traveling wave.
difference.
Okay.
Of course, this is sort of a temporary, I know.
No, I'm just saying that's
Okay.
One good question. Is the trace of W times T equals 0, is it equal to A n of 0, U 0? But if you go back to the previous, just asking the question whether the trace of W times
Yes,
T equals
yes,
0,
yeah.
the initial conditions for W at T equals 0,
Yes,
it's equal to 0,
yes.
and is that the trace of A of, is that equal to A n of 0?
Basically, U, okay?
Sorry?
Basically, U is very important.
But is it? No, I'm like,
Okay, here, okay?
yes.
Yeah,
And W times T equals 0 is 0,
yes.
but is A of n equal to 0? A of n 0 is equal.
Why?
the monotone decrease.
Right. So, so we have this system where there is a kind of a discontinuity for the. This is some kind of strange initial condition, isn't it?
Why?
Discontinuous.
Why discontinuous?
Okay.
Okay, well, okay, so maybe later.
Talk to you later.
Yeah. Okay, so now, so I emphasize about two, different types of instability occurs in order to this one, okay? And then I will check. So in the experiment, I told you this is a sort of, a steady cluster, and this is moving this way, and that is generate a new, cluster there. So this is experiment. How is our model? So our model here, so same thing is this U, and this here is moving here like this, and then so U plus W. This is the U plus W here, and look at here. This is at first here, and the sum of them is stay there, and this is moving this way, and you can get a new cluster. So, in a formation point of view, we can have very nice, dynamics similar to this one. And I will show some. Wait a second. I don't know why this is. It's very strange. Okay, yes. So this is U, and this is W. Maybe you stop here. So this is so any U tend to W. That was nothing. So this is moving here, and this is sort of the trace. Okay, and you can see this is at one point of inoculation, and U is so like this. Okay, W is like this is sort of the trace. And also, I told you in experiment that the new spot appears. Also in a model, also this new spot appear, depending on this whites. Okay, so this is please ask me why I can find this kind of process. This is just from mathematics. At first we said this is this axis is N naught, okay? And so N naught, and this is a kind of a planar wave. And when N naught is here, so this planar wave is destabilized, and we can get this kind of branch. This kind of branch is correspond this one. And this is also we have a secondary bifurcation occur by the Hop type, so we can get this one. So our rectangular the pattern is given by the two different instability occur. Okay. What is this? Okay, okay. And still N naught is increasing. So what happened? So this is only W. So you can see no more ordered pattern. It's a very strange pattern. Okay. So it means rectangular lattice pattern breaks down. And if N naught is still increasing, does hexagonal lattice pattern appear as experiment suggests? But this is very difficult for me, so I had no idea at that time. But look at, I told you here, this is explained by Sakurai, very dirty pattern. But look at here, so this is like a concentric ring pattern appear, but here is a sort of hexagonal pattern. It's a sort of coexistence. Of course, he did not publish this kind of pattern because it's a bit dirty. But this is very good information for me. When in his experiment, the concentration of from 10 millimole to maybe this is 8 or 7, decreasing. So they showed this one. Okay, so I coming back to my model. So this is N naught is here, I told you before, and N naught is 3.0. So we can have very nice, planar but oscillatory propagating wave. So in one case it's like this, okay. So at first in this case is if N naught is decreasing, in the previous one N naught is increasing, but here this case is N naught is decreasing. So primary bifurcation is like this, Hop bifurcation. And then still decreasing, so we have very nice hexagonal one. So this becomes the instability occurs like this. And I will show a movie. So maybe it's better to just now stop here. So W is a 10 minutes. So like this, very nice alternate pattern. Okay. So in order to get the rectangular pattern, so I'm moving this way, but this is from this way. Okay, and also this is very interesting. So when you change the length, this one is 2.4, 3.0, 3.6. So at first, in this case, it's 2 spots, And this is this distance increasing, but when L1 is 3.6, new spot appears. So it means that if this distance is increasing, so new spot appeared. They keep the almost same distance. Okay, so yes, here is so so in this case is N naught is increasing here, so like this, but in this pattern is N naught is decreasing like this, but I don't know this one. Okay, it's a very hard problem for me. Okay, so maybe 6 minutes. Okay, at first I just said UCN system is the closed system, and we have the very nice mathematically nice result. So nothing happened. But when you consider about W, the W is given by this one, then you can get this kind of pattern. Yes?
I change my initial condition for W to be some arbitrary function of X. It doesn't change the evolution of U, N, and C.
Yes, but it's the integration here.
Yeah, I know, but then I just so I can my WT of X converges to that thing that you've written down, W infinity of X plus my initial condition, which can be arbitrary, but it doesn't change the evolution of U, N, and C.
No.
So I can get whatever. So my pattern for W infinity could be anything that I like, just by changing my initial condition for W.
I don't know.
I can.
Okay.
That's correct, but the point is you start out the experiment with no W's, right? So that gives you, from the experimental side, the appropriate initial condition for it.
Well, we don't know what W is at time t equals 0, do we?
Well, sure, you
doesn't affect the evolution.
We inoculate at a point, and then they spread out due to growth, etc. So initially, you assume you don't have any of these inactive cells anywhere in the domain.
But you could have the mathematical model with U, N, and C. It's the same mathematical model, and then you can put into your initial condition for W anything you like.
Right, they never go away, so they just sit there. But the W's don't do anything to the problem.
So W
Record of what you're using.
W never ever influence of the system. Just look.
Crack. I mean, if you had W still consume nutrient at a low rate, then it would have some effect. But basically, your W is just recording what the U concentration was.
This is W sort of recorder of the U and N.
I think that's my observation. Kind of encoded into it's encoded into the 3x3 system that you can obtain.
Okay, so let me. Okay, yes. Anyway. Okay, now so I have 4 minutes. So maybe you are interested in the this pattern, chevron pattern. Okay, the final question is, by using our model, can we explain the reason why chevron-like pattern occurs? Okay, but so we have not yet been able to answer to this question. Instead, can our model generate chevron-like pattern when some parameters are suitably specified? Okay, so now forget the biology. We think about model. Okay. And the question is, can our model generate chevron pattern? Okay. And then, as I told you, in this pattern we have two kind of the typical pattern. One is so like this. Okay. The other is a very nice checkerboard pattern. And for me, it's at almost 3 years. I always, wanted to have this kind of pattern, always. So like a star shape. But it was mistake. Okay. So now this is very important. This pattern is very important. That's my idea. And then, okay, so let us look for a suitable parameter value to exhibit tight and regulated checkerboard pattern. Maybe I just skip some parameter, so it means the following. So this is time axis. So this is U, this is W. So you can see very nice checkerboard. Trust me to find this pattern by using the suitable parameter values. And it's very similar. This is also hexagonal. This is also hexagonal, quite similar. What is different? Different is following. In 1D case, as I told you, in this case is so like this, oscillatory. But here is surprising. Is just a very simple, front wave. Quite different. Also here, this is very important. In the hexagonal one, if this the length is increasing, so I told you this is at first increasing, and then if the length is larger than some critical value, then we have a new spot appear. So this is this case. But in this case, is a very tight checkerboard pattern. Is the same thing. It is increasing, but at that time, in this case, it's 2, and moving this way, and this is almost this is 6, 9, 2/3. So this is 3. But here you can see this oblique. Understand this oblique here. So they don't change dunk formation. So only so like this, okay. And but this one is a little bit, the bigger, and the new spot appeared. And then I will show. Okay, so 2 minutes.
Yep.
I will show some. Simulation. This is only 1 point here, but also this quarter, and this is just indication, no meaning. And this is U, this is W. So here, this is very much, the irregular pattern appear, but almost, ding. And we'll stop here. How is that, W? The W is a sort of recorder of U and N. So can you see a kind of very nice chevron pattern?
Well, this is what the talk this morning was about. You're basically doing diffusion on a growing interface. If you put your system on a hemispherical layer of agar or a saddle-shaped layer of agar, you'd get a different philotactic pattern.
Yeah. So this is just a bigger size, okay? So like this. Okay, so now 1 minute, sir. What is the mechanism behind the occurrence of such a chevron-like pattern? Okay. So I can tell you the answer. Okay, so this is the same. Simulation, but the different is the initial function is a sort of the diamond symmetry here. It's very artificial and intentionally. So it means we have a sort of the symmetric line here, and this is sort of a symmetry. This is also symmetry. Okay, very much artificial, of course. And then I will show. So that no more ring, okay? It is sort of straight line like this. So maybe you can see, maybe stop. Okay, this is very, tight rank formation. Here also, and this is symmetric. This is symmetric. Okay, So you can imagine this is sort of illusion. What that means illusion means that it's very, this distance is very close here compared with other. So you can see, this kind of pattern, okay? That's illusion. And then so it's sort of here. So this is a very nice, checkerboard or crystallized pattern. But here is a sort of the grain boundary or a defect of crystallization. And we can see this pattern. But the important thing is that this pattern is very important. That's my message, okay? So it's sort of the chevron-like pattern is a kind of illusion. Important thing is here. So this is final one, and at first when we see that this kind of pattern, important thing is the very stable checkerboard pattern. This is very important. And if depending on the size, they only change direction, oblique one. And second one is a growth pattern is generated from the one point nucleation here. So in the previous, this is it from this one, okay? But this is 1 point. And another one is spatial fluctuation occurs. That's why bacteria generate crystal structure in a self-organized way, and as a consequence, chevron-like pattern appears as an illusion. This is my understanding. Thank you very much.
So are there additional questions or comments? None. I guess we covered
I
that.
have one question. So you say it's an illusion, and basically the occurrence of the chevron pattern being due to fluctuations.
Yes.
Why do I have such a regular length scale which is appearing in the pattern, in the chevron pattern?
That is that's another problem, because so in this case the important is this angle, okay? This is very important angle. But I don't know mathematically. It was favorite angle, maybe 60 degrees, very good.
Any further? Okay, so this is the last talk of the day. You're free to do whatever.
Anyway, thank you for your patience.
Thank you.